Good morning. Welcome to Krishna's classroom. We take up another episode of Riemann integration. And this is probably the beginning of concluding our discourse on Riemann integration. We have completed the details already, but now what we look forward to is a review. Whatever we have done is an incredible achievement in the forward movement of ideas in mathematics. But certainly we would like to see whether that is good enough, or do we have to go beyond this and look at the concept of integration. So let us recall, what did we do? We started with the conventional notion of what is called antiderivative of certain nice functions. We successfully related this to the integral of the area enclosed between the graphs of the function and the ordinates. And having introduced the concept of integration as computing the area, we finally close the circle by showing that at least in some situations you can recover the function that we have started with through differentiation from the newly created function, thereby realizing that the newly created function through integration, or what is called the area function, which I introduced in the beginning, is in a way the antiderivative of the given function, but with a lot of qualifying conditions. Now this is what we look at carefully. So we revisit our fundamental theorem of calculus and then start making remarks on that. So let me just recall the fundamental theorem of calculus. For the sake of reference, let me just write this. We take a map from a compact interval AB to R, a real valued function, bounded and Riemann. Let Fa be equal to 0 and Fx is defined by a to x dt for x belonging to A. Then the following, then the first inference is that F is uniform. Two, if F is continuous, at x belonging to AB, this is conditional. Capital F is differentiable. At x and f derivative of x is a local product. Okay, but it is subject to the condition. The third condition is that if g is any differentiable function if g is any differentiable function such that g derivative of x equal to f of x, g derivative of x equal to f of x, then for every x, y belonging to AB, gy minus gx equal to integral x to y ft. So here again there is a conditional. Now we make an observation. Let us revisit one of the examples that we did earlier. Suppose we have the function we take f of x to be equal to, so we take the interval to be 1 to 2, fx equal to 1 1 to 0 to 1 2 over so the function is defined from the interval 1 to 2 to and we observe that f has a jump discontinuity at equal to 1. Now, let us, so it is Riemann integral, of course, f is Riemann integral. On 1 2. Let us compute the Riemann integral. The Riemann integral of say let us call this fx. Suppose we define fx to be from 0 to x then fx equal to x for over the interval 0, 1, and this is equal to two x minus 1 for x belonging to 1 to so at x equal to 1, you see that the function takes the value 1 from here, and the limit of this function from the other side is going to be simply x equal to 1, you will get 1. So you get a continuous function. In fact, this is the sort of function you get. This is 1, side is 1, and then of course from 1 to 2, you see that at 2 is 3. I mean, this function we have considered earlier. So it's a continuous function. Well, this is the graph of the function. It's a continuous function, and the original function f we can define. So this function has the graph. It is 1 here, 1 over the interval, and then 2 over this is 1, so this is 2. So we can define it. I defined it as 2. Okay. So I define it as 2 here, and this point. Okay. So that's a function, and this is the function y equal to f of x. And this is the graph of this function. So this is the graph of y equal to capital F of. So observe that f is continuous. On 0 and is differentiable everywhere except at x equal to 1. So it really satisfies this condition that wherever f is continuous, you see that f derivative is equal to. So the condition 1 is 1 holds. What about 2? 2f is not continuous, therefore a capital F is not differentiable on the whole interval. But capital F is differentiable everywhere except at the point x equal to 1 where small f has discontinuities. Now this is the problem. Okay. Now what you want to observe is that suppose I change this function. Suppose, let me introduce, let f1 be defined by one for x belonging to 0, 1 and 2 for then you see that f1 is f1 is different from f1. So these two functions are different at the point x equal to 1. And one can easily verify that you end up with fx is also equal to integral 0 to x dx. Therefore, if you were to consider capital F as the antiderivative of small f, then it is also the antiderivative of f1. If you were to define the relation like this, okay. Now, in fact, more generally, one can even introduce an f2 1 on x belonging to and some constant c at x equal to 1, c finite of course, then 2 on x belonging to 1, 2, which means, see, f2 is discontinuous at the point x equal to 1 if c is different from 1 from both sides. Okay. Even then, you will see that fx is equal to integral 0 to x. Therefore, fx is also capital F is also antiderivative of f2. In fact, you see that by varying values of c, keeping it finite, you can get several functions, okay, for which capital F will turn out to be the antiderivative. Therefore, what is a causality? What is a causality is that the relation between a function and its derivative or a function and its antiderivative is not well defined. Okay. It is not that given capital F, given small f, it has a unique antiderivative. So by writing the function f at the points of discontinuity, but still keeping the function Riemann integrable, you can get the same function to become the antiderivative. So this is one of the problems that you encounter. Of course, it is not there the moment you take small f to be a continuous function. The moment you take small f to be a continuous function, this problem does not exist. And you see that is the first part of this. The second statement of the theorem, if f is continuous at a point x, then capital F derivative is exactly equal to f of x. So you can recover the function actually from capital F, whereas the function f1 or f2 or f cannot be completely recovered from starting from the function capital F. Therefore, it is not absolutely true when you connect these two to the notion of antiderivative. Now, this is one of the difficulties that you encounter. Okay. In short, we see that the two functions capital F and small f are related by the relation, that is fy minus fx over integral from x to y ft dt if and only if capital F is differentiable and f capital F derivative equal to Fx. So let me write it because these are small little things which you may need. So I'll just write that. So in fact it's a content of this theorem that we are writing. So in fact this is what we have. We have the following. A pair of functions f and capital F on AB for f belonging to a Riemann integrable class on AB. This notation we introduced earlier are related by the relation by the equation f of y minus f of x equal to integral x to y dt if and only if capital F is differentiable and capital F derivative of x equal to f of x. In fact, in this context, dimi, that is, will you say dimi? In the year 1878, introduced 4 concepts of different concepts of derivative. At a point of a function at a point called the dimi derivatives. You can look at the details of this sum and product analysis. Now, then he showed that for a bounded function f from an interval AB to real valued function, the function ft dt has all four derivatives. Here we are tacitly assuming that f is Riemann integrable. It's bounded. All of them are bounded. All of them are bounded. Integrable. And f y minus or fx minus f a is equal to integral a to x df where df is any one of the four, any one of that is exactly what the sort of relation I pointed out with the example that we have looked at. Therefore, what we have broken down is the sort of unique relationship between, possible unique relationship between the small f and capital F connected through this integral. Okay, so such a relation cannot be really asserted. Okay. Then he also pointed out that the condition f dash is integrable is a necessary condition. In fact, he pointed out that the condition f dash is integrable is in the fundamental theorem is a necessary condition. In fact, so this is what one of the fallout. His conjecture was, he also conjectured that there exists a function, yeah, such that f is, there exists a function capital F from AB to R such that capital F is differentiable. But F derivative is not bounded. F derivative is not bounded and hence not Riemann integral. Which means he says that there exists a function capital F such that F derivative exists, but F derivative is not bounded and therefore it is not Riemann integrable. So this possibility is bounded. And in fact, one can give an example, very simple example, but possibly worth looking at in detail, because these are the examples which, see, in analysis it is the examples which drive the theory, or new theory is created when you pursue examples. So what you have is, let us look at the example. So consider the example. Fx defined by, consider the function f of x defined as x squared sine 1 upon x squared if x not equal to 0, well defined, and equal to 0 whenever x is equal to 0. This is a fascinating equation. We have a similar wildly oscillating functions which give you some very interesting insight into the problems that you encounter. So let us investigate this one. Now first of all, you observe that it is defined at 0, as we have defined, and the function is continuous. That is because sine 1 by x square is a bounded function. Okay. Therefore, we observe that we consider this function on 0. Then f is continuous. We also show that the derivative exists. Okay. So when you stay away from x, okay, let us look at what the function is all about. If you look at the graph of this function, this is yeah. Okay, let me just take this as 1. This is the point 1 to 1. So equal to x square is this. And then you see that we go for its reflection. -1 and then beyond x. Okay. So this is y equal to x squared. So let us not follow this. We are interested only in the level 0. Here you see that what are the zeros of this function? First, x equal to 0 is a 0. But then 0 of this function, other zeros of this function are the zeros of sine 1 by x square. So the zeros of are x equal to 0 and the zeros of sine 1 by x square. And where do you have sine 1 by x square vanishing? So this is, that is at 1 by x square equal to 1 by x square equal to n pi, or x square equal to 1 upon n pi. If you take the positive square root of this, x equal to 1 upon square root of n pi. Okay. So other than 0, these are the points. Now you see that if you look at these points, so n equal to 1, you are at 1 upon root pi. 1 upon root pi is somewhere, is certainly greater than 1, so it is somewhere here. Then you have 1 upon root 2 pi. So root 2 pi will be, okay, 1 upon x square equal to 1 upon 2 pi is 1 point something. So again you have something somewhere here. I think when n equal to 2, you get 1 upon so 2 pi okay. So it is less than this. So you divide by this. Now you can actually compute this. So is this, what about 2 pi? Is 2 pi equal to some 2 into approximately. So it is 44 by 7. Something. So square root of 5 point something is going to be 2 point something. Therefore, this is going to be this time. So 1 upon. Then of course you have 1 upon root 2 pi, 1 upon okay. So this is going to be 5, so it's going to be 6 point something actually. So you have got 7, so approximately 6 point. What? Well, it doesn't matter. So you see that if you take the square root of this is certainly lying between 2 and 3. Therefore, x lies between the square root of this. So this is 1 by 3 and 1 by 2. So you have got 1 by 2 sorry, I think I have marked this wrong. So it's around 1 by 2 and somewhere here. So this is 1 by, so somewhere, yes, 1 by 2 pi. This is 1 somewhere here. This is 1 by 2, 1 by 3. So it is somewhere here, 1 by 1 by 2 pi is somewhere here. Okay. So these are the zeros, and then you have got all the zeros coming here, more frequently disappearing. So the graph of the function is going to be something like this. Something like that. It's just immaterial what it is. It becomes frequently, so you can actually do some little bit of approximate computations to get that value. So I think that's something which you can do. I leave it to you for the computation. It is immaterial for our conclusions. So for our conclusion, what we look at is this. So look at this function. Now let me compute the derivative of the function. The derivative of the function is at x equal to 0. You see that f derivative of 0 equal to 0. That is quite easy to do. You just divide, take this, it just takes the 0 value, so minus 0 divide by x. So you get x times something this, and this is a bounded function, therefore it's 0. Now so when x not equal to 0, compute the derivative. F derivative of x is equal to, you take this, which is 2x sin 1 upon x square minus 2 minus 2 by x cos 1 upon square. This is the function. And you can see that for x not equal to 0. So for x not equal to 0, this is a nice continuous function. The dash is continuous. For x not equal to 0. What happens to f dash as x tends to 0? As x tends to 0, you see that this term goes to 0, but certainly this term goes to infinity. Okay, this becomes unbounded. So f dash is unbounded. F dash is not continuous at x equal to 0, and f dash is unbounded on 0. Therefore, which implies f derivative does not belong to now this is not Riemann integrable, it's an unbounded function. Okay? Therefore, f dash is not Riemann integrable. And this is what Dini had been predicting. There is a function capital F which is differentiable everywhere, but f derivative is not bounded and hence not Riemann integrable. Okay, right? So you see that we are running into deeper and deeper waters, and this pursuit of this function, in fact, was carried forward further in another example, which we shall look at in some detail. Okay, so we look at the Volterra's example. It's a fascinating. So where have we reached? We have reached a place where capital F is well defined, but f derivative is not Riemann integrable. It's a nice uniformly continuous function, but it's not Riemann. Its derivative is not Riemann integrable because its derivative is continuous everywhere except at a point, and there the derivative becomes, or in the neighborhood of that, the derivative becomes unbounded. There is a discontinuity for that, and it becomes simply unbounded in the neighborhood of 0. This is the problem, therefore it is not Riemann integrable. Now we look at this fascinating example. Before that, let me make some remarks. Before that, let me recall the Riemann function R. We have introduced earlier. Now we shall define. So this is the Henkel's construction. He defined a function gx integral 0 to x. Recall RT was a wildly fluctuating function with its discontinuities on the interval 0 to 1, infinitely many points where the function is discontinuous. It's a wildly fluctuating function which has been constructed with say the function y equal to x defined on minus half to plus half and then so on. So you go through the construction. I don't think I have discussed it in detail. However, the function is an integrable function. It's a bounded function, and you can show that it is an integrable function, so it's a Riemann integral. So this gx is a continuous function. Everywhere, but not differentiable at an infinite set of points. In fact, this actually was a startling example at that point of time, because this happened way back in when the concept of integration was evolving. This was a startling example. So at that time there was a belief that if you take any continuous function, the derivative exists everywhere except at finitely many points. This became a pointer to show that the sort of the feeling all continuous functions are differentiable except possibly at finite limits. Which is in fact not true. In fact, later Weierstrass came out with an example of it. In fact, it's a beautiful construction which we have discussed again. Example of a function which is continuous everywhere, but nowhere differentiable. So, the scene was chaotic. It changed some of the conventional notions that people, they thought that all continuous functions are differentiable everywhere except at finitely many points. And even this was later completely, shattered by the famous example, which Weierstrass constructed, where he showed that there exists a continuous function which is nowhere differentiable. This also we have discussed in detail. And therefore, the connection between the function, a given function and its integral became very hazy. Because if you are given a continuous function, can you recover that function in the form of an integral of with the Riemann concept of Riemann integration? This becomes difficult. Okay, so the sanctity of the antiderivative became all questionable, or the fundamental theorem of calculus is now a very restricted theorem connecting the function and its derivative, and even the differentiability is questionable. And you see that only if a given function is continuous, its antiderivative or its integral becomes differentiable. Okay, so this is not something that can be taken for granted. Now we can look at the the construction by Henkel. Because these are probably worth looking at, because you see that it's this kind of fascinating functions which pushes the mathematical analysis forward, or which has pushed the mathematical analysis forward, and to ask very interesting questions. Look at Voltaire. Here we start with a fundamental function f of x equal to x squared sine 1 by x for x not equal to 0 and equal to 0 for x belonging to, it's a real valued function, very nicely defined, and you can easily see that it is continuous. And even f derivative f is differentiable everywhere, and you see that f derivative of x is defined to be, is turns out to be 0 at x equal to 0 and equal to, you differentiate it, you will get 2x sine 1 upon x minus to the power minus you get cos x or x naught. You see, so there is certainly problem for this function at x equal to, in the limit when x tends to 0, this function has a problem. Okay, so this f dash is not continuous. F dash exists everywhere, but f dash is not continuous at x equal to 0. This is it. Now, starting from this function, we construct a function on the interval AB. So let us start constructing a function on the interval. So this is our mother function that we start working with, and from which we generate a new function on the interval, and then use that to define something on the interval 0 to 1 or something like that. Okay. So we start the following. First step. We are interested on the interval 1. So we define by FA define it as follows. It is actually constructed from this. When a equal to 0, you get this function. So you get this is equal to, yeah, I think it may be worthwhile to look at the graph of this function also. So let me write down this and then after that I will go. So this is actually shifting this function to a. When x is not equal to a and this is equal to 0. This is actually the translate of f. Okay. So let us see the graph of this function. If you look at the graph of this function, again you see that the function oscillates between x square and minus x square because of this factor. The oscillation comes from this factor, and as x goes to 0, it rapidly oscillates. So you take 1 here, 1 here, and this, you have x function here. And you see that what are the zeros of this function? The zeros of this function can be easily computed. So it is 1 by x equal to n pi, or x equal to 1 upon n pi will be the zeros. So 1 by pi will be roughly 1 by 3 or something like that. Okay. So 1 by pi, then this is half. 1 by pi is somewhere here. Then 1 by 2 pi, 1 by 3 pi, and so on. So what you have is a function which oscillates here. Okay. The function which is coming down and then going. This is 1 by pi. So it just this shoots up like this. Because after between what you call n pi and between pi and 1 by pi and infinity, the function is positive. So that you can see something like this and oscillates to the right. So just have a feel for that function. Therefore, what about this function? So this function is defined for some a to a onwards. So you have something like this. At x equal to a, it is 0. So a plus pi and so on. Okay. So this is going to be the plus half, and this point is function equal to 1. It's a value 1. So what happens? The function becomes negative between these two. It just becomes unbounded, and then you want this part. This is the function. Okay. It's a nice good function, except at the point A. Except at the point A, it's a nice good function. Okay. So the next step is, having got this function, we will now define the following. So the step 2 is, we don't define it on the whole interval a to infinity or anything, but we are interested on the interval a to b. So what you have is, you have the interval a to b, then you take the midpoint of that, a plus b by 2. Now we define alpha a to be the supremum of x lying between a less than x less than or equal to b by 2, and f derivative Now, where does the derivative vanish? F derivative of x a equal to. So, it is at the points where the function attains the maximum or the minimum, and such a minimum is, see, it depends on the point b. So, a plus b by 2. So, you will get some point to the left of it where the function is derivative. That is the supremum point that you are getting. So such a supremum exists, because you see that the set of points where f a derivative x equal to 0 is bounded above by a plus b by 2, because we are only interested for all x, this is, and therefore the supremum exists. So alpha a exists. Okay. Now we define another function drafted from this. Now see, this construction we have to go through very carefully, because it is at the crux of working out the or looking at the construction. So first understand this function, and then you understand this function very well. Then you see that this alpha a, what it is. Alpha a will come because of the oscillation of the function. The alpha a will come at the place where the tangent to the function becomes, the slope of the tangent becomes 0, or the tangent becomes parallel to the x-axis. And that happens at the points of minimum and the maximum. Okay. So you just take the last point where you have the minimum below a plus b by 2. That is the. Now you define another function. Define this is the notation f a b. From the interval a b to r, you define this as follows: f of a comma b x is equal to f a x if a less than x less than or equal to alpha. So it attains a maximum or a minimum at this point. That's the point. This is the last extrema that the function attains on the interval a to a plus b by 2. Then you define the function to be fa at alpha a. It's a constant function. If alpha a is less than or equal to x less than or equal to b minus and then you extend this function f a b plus a minus x if b minus alpha a minus a less than or equal to x. Okay. So we divide this into three pieces. What are the pieces? Let's analyze this. So it's an interesting. So we are now working on the interval a to b. And we have the midpoint a plus b by 2. And then alpha a somewhere here. Now we divide this into three portions. What is that? This is actually b minus that means you have a distance. See, the distance that you have here from a to alpha a is alpha a minus a. And you divide from this or subtract from b alpha a minus a, so you get a b minus alpha a minus a. So that is this point, and this is the. So you divide the interval a to b as three portions, namely a to alpha a, then alpha a to b minus alpha a minus a, and then b minus alpha a minus a to, so three portions. Okay. Now what we do is we take this function as f(a)x as we have defined here, Now you see this is a point where the function attains a maximum or a minimum, depends. So if it attains a maximum, then it is turning around there. So you get a tangent which is parallel to the x-axis, and from there onwards you define the function to be f(a) alpha a constant function, and it goes up to b minus alpha a minus a, and from then on you define a function. Now I just show that if y is some point in between, then you see that you have the corresponding point b minus y minus a. Okay, so at b minus y minus a, the function takes the same value as the function takes at y. So let then b minus a y, oh sorry, b minus y minus a belongs to this one, b minus alpha a minus a, and to this is what we observe. Let's see this. Now we claim that f of, we will calculate at the point, at this point. Let us compute this. What is this? This is equal to f(a) evaluated at b plus a minus at this point. That is, what is this point? This point is minus b minus y minus. What is this? This is equal to b and b cancels out, a and a cancels out. And this is equal to, therefore you see that FAB is about A plus B. That is in fact a reflection. That's the symmetry. So you have it oscillating here widely and then becoming a constant function on this and then again oscillating here. Okay, so this is the function that you get. So wildly oscillating function at A and B and constantly between, what is that, alpha A to this. And it oscillates at both the endpoints. So this is the sort of function there. Okay. Now we make some we also observe that FABX is equal to F of B. We start with B around the point B and then oscillates. So because you see that upfront you have this defined here as well as defined on this side. Okay, so you have the oscillating function. This bounded like this, just goes up. This is the sort of function. So this is equal to minus FB okay. So this is something that you can work out. Moreover, we can use some estimates. There are some very nice estimates of this function. So I think this is where you will have to put your hand and then work out everything. So it is these kind of little things that finally pushes ideas in analysis forward. Okay. So you can easily see that this is the following. So therefore this implies mod f a b on the interval a b is less than or equal to maximum of b minus x whole square and a minus x whole square. So it depends on where you choose the point x. Okay. For every x at the endpoints a and b, this function is 0. Okay. So let's see. We also observe that f a b is differentiable everywhere. And you can compute the derivative easily, and you observe that you can compute this f a b x derivative is less than or equal to twice b minus a plus 1. So that actually, when you differentiate this, you get 2x. See, this is a sort of function 2 into x minus a sine 1 by x minus a. This is a tangent. Minus, you have cos, and you see that this is bounded by 2 and this is bounded by 1. That's why you get this. Okay. So in fact, this follows from, in fact, f a b x is equal to twice x minus a sine 1 upon x minus a minus cos and then of course you can get the derivative on the other side, which is easy. So okay. So at n pi, okay, so that is actually a plus x minus a equal to 1 upon n pi. So x is equal to a plus 1 by n pi. So choose n sufficiently large such that 1 upon x minus a equal to n pi, and hence at this point at this point f derivative this is equal to minus a equal to so you want 1 by this. If you work out what happens here, so you see that this term is 0 because of this factor. You get sine n pi, so it is 0. It is this term that comes out, and this term is bounded between, in fact it is going to be either plus 1 or minus 1. Therefore this is equal to plus 1. So we do not know, it depends on n. Similarly here, B, f derivative oscillates between minus 1 and so this is the estimate of the derivatives. So we have these estimates and we shall need to use them properly. It is because of this term, this is the term that is going to be relevant at a plus n pi. Okay? Or the corresponding points on the other side. So you get this term either becoming plus 1 or minus 1. Here this function vanishes by that place. Okay. So it's infinity. Because you see that this particular term becomes important and this becomes, see these points will decide what is going to be the value between, so it's just going to be fluctuating between minus 1 and plus 1. Okay. Now what we are doing is, we have not completed the construction. Now in step 3 we are recalling the characteristic. See, our strategy is the following. We are taking the interval say 0, 1. So this is a general construction that we are going to use. So we are now interested, actually the actual construction is on the interval 0. Now we have got C alpha. So 0 less than alpha less than 1. And we have C alpha is contained in interval. This is the characteristic. This is the characteristic. Now I think I will stop here because it takes quite longer from here to estimate and so on. So I will continue with the construction tomorrow and then work out the details of the function. So our strategy is the following. Okay, we define a new function, a function which is 0 at all points of the Cantor set. Elsewhere, what happens is, you know the construction of the Cantor set. The construction of the Cantor set is, you take the middle, there is an interval. In the first stage, you drop an interval, then you get two intervals. Again, you take the middle of that and drop an interval, and so on. So we do this infinitely many, and you get a set of, eventually you are left with a set of points called the Cantor set. Now we have already discussed in detail the properties of the Cantor set, and we will make use of that. Now we start constructing a function. For example, if you have an interval in which only the extreme endpoints are the points of the Cantor set, and the others in between, there exists no points between the Cantor set, then where we consider this as an interval AB and define this function. So it oscillates at both the endpoints, and it's a continuous function, it is differentiable everywhere, but the derivative is not continuous at both the endpoints. So we patch up this, we define a function of the whole interval 0, 1 by patching up these kind of functions. Okay, and then we make certain observations on this function. In fact, we show that this function is 0, if derivative is 0 for all x not belonging to C alpha, and f derivative of x is not continuous at all points C alpha. We know that this, after proving this function fluctuates infinity often near a and b. And we show that f derivative is not Riemann integrable. Capital derivative is not Riemann integrable. So we go through this construction in our next phase. Okay. Thank you very much.